Hey, how's it going today? My name's Joey Miyako, and today we'll be talking about hydrogen nuclear magnetic resonance, or NMR, and 13 carbon NMR spectroscopy in order to uncover an unknown structure. So first we're going to talk about hydrogen NMR spectroscopy, and then we'll get to 13 carbon NMR spectroscopy. So the first thing to think about is what exactly is hydrogen or 13 carbon NMR. And basically what it is that they're going to take the molecule, they're going to put it into a magnetic field, and based on when the molecule flips, spins, so let's say it's spinning this way, and once it flips this way, that'll create a measurable component that we can put on our graph here. And that will allow us that based on different functional groups, they will flip at different points in time. And based on this, we can discern what functional groups may be present in our molecule. Okay, so in addition to this, what it'll also tell us is what's called the spin-spin coupling pattern. And so if we take a molecule, say, like this, let's make it easy. And each one has one hydrogen. And so, by the way, this is measuring when the hydrogens flip, specifically the hydrogens. So let's say it's our molecule that's like this. And hydrogens themselves have a magnetic field that influences each other. So let's say if we're thinking about this one here, this hydrogen is going to influence. So in order to determine the spin-spin coupling pattern, we're going to look at all the adjacent hydrogens. So we're going to go to that hydrogen's carbon. We're going to go to any carbon that's adjacent. So here we only have the one carbon. We're going to go to this one, and we see that it has one hydrogen next to us. So using the formula N plus 1, we have one adjacent hydrogen. We're going to add 1 to it, and that's going to equal 2, I should put peaks. Here we go. That's going to be 2 peaks, okay? And that checks out. Look, here we have a one adjacent hydrogen. We should have a doublet, 2 peaks. And this continues. And so you can take the number of peaks that you may see in your data, and you can pull that back to say, okay, like I have a quintet. I know that I have 4 adjacent hydrogens. Now that could be on 4 carbons. That could be on, well, it couldn't be on 4. It could be on 3. It could be on 2 carbons. We're not sure about that, but we do know there's that amount of adjacent hydrogens. So basically, we can take this information and we can apply it to figuring out what exactly is going on with our molecule and what may be present. So now we're going to look at the HNMR of our unknown molecule. So here, the first thing that we're going to look at is the number of signals, or the number of peaks. And here clearly we have 2 peaks. Okay, we know this is 2. So we know there are 2 environments that our hydrogens could exist on. Now, what we don't know is how many hydrogens are from this. Well, we don't know yet. We'll get to that with integration. But we do know that there are 2 peaks, which means 2 environments. Okay, and we clearly know that there must be more hydrogens in this environment than there are in this environment. But again, we'll get to that more later. So we know that there are 2 here. All right, so number of signals 2 equals 2 hydrogens. Next, we're going to look at our chemical shift. Now, based on our graphic back earlier, if we remember, up here in this range, we had our carboxylic acid, O to OH. So this is pretty clearly, this is probably pointing to carboxylic acid. Okay, so that's a big hint to the structure of our molecule. Now this is a little trickier because this has several options, and we're going to need to compare this with our 13 carbon NMR, as well as if we're doing other kinds of data, we could also compare it with the mass spectroscopy or with the infrared spectroscopy, which if you need help with, there's another video by myself that may help. You check out my YouTube channel, it's there. So this one's pretty clearly due to carboxylic acid. This one is in the range. It could be an ether, it could be an alkyl halide, so it could be like a carbon to our X. It could be, let's see, and it could be an alcohol also. That's a possibility. So based on what we see here, it could be any number of these things for this one, as well as we think we have the carboxylic acid here. All right, and then the next thing we need to look at is splitting. And apologies for this formula. This should be just n plus 1, just making sure you're paying attention. And of course, we have no splitting here. So of course, we'd have 0 plus 1 for each peak, which just gives us 1, which is our one peak. Apologies, it should be 1 equals 1 plus 0, 1 minus 1 equals 0. Okay, and so that's our 0. We have no splitting. There are no adjacent hydrogens, which is another important thing to consider in how our atoms are going to be arranged. All right, the next thing to look at is integration. Now, integration is a value, the data that's given back. And actually for this one, we got kind of a strange integration. Typically for the integration, you're going to look at the values that the data gives you, and you're going to be able to make a ratio with that. So for example, let's say this one was the 150 here, and this one was 600. You're going to take the smallest, there are 2 peaks, and you're going to take the smallest one, even if you had 3 peaks. Let's say there's a 150, a 600, and a 450. Okay, for example, you're going to take the smallest one you have, and you're going to divide it into the larger ones. And by the way, all this data is from SDBS, so you can go check it out yourself. It's very cool. So you're basically going to take the smallest one, and you're going to divide each of these, including itself, by that number to kind of figure out the ratio. So 150 over 150 equals 1, 450 over 150 equals 3, 600 over 150 would equal 4, and basically that would tell you the ratio that the hydrogens in this environment, there's going to be one of them for every 3 of these, and one of these for every 4 in these. Okay? But here, it may be based on the hydrogen bonding with the carboxylic acid. I'm not sure why SDBS gave such a high value for this, but it certainly is not let's see, 700, about 7-to-1 ratio, which would be projected by this, as 1,000 is the max value that you can get. Okay, so in reality, we're going to find it's going to be more of a 2-to-1 ratio between our hydrogens in each environment. Okay. And by the way, I should quickly mention the different environment aspect of this based on HNMR. So if we go back to our example that I pointed out, where you have a C to a C to an O to an O, and you have the H here, it's pretty clear that both, if you kind of think about the environment that these H's live in, it's exactly the same. They both touch a carbon. To the next side of them, there's a carbon double bonded to an oxygen. There's carbons double bonded to an oxygen. These guys' peaks would show up on the same spot in the H. It might not be there, but they would both be in the same exact spot. Now, if we had, let's say if we go up here, and we had a carbon to double bonded to an O, and we had an H, and then we had, let's say, we had 3 H's. All 3 of these H's would live in the same environment, but this environment would be different than the environment that this guy lives in, okay? Because this guy is closer to this oxygen, which is more electronegative, okay? So we also got to think about what kind of lives are these, that's the way I like to think about it. What kind of lives are these hydrogens living, okay? What's their environment like? Okay, and as we saw before, that this one may be living a carboxylic acid life, and this one could be living an alcohol or an ether or an alkyl halide kind of life. All right, so now we're going to move on to our 13 carbon NMR. And it's the exact same kind of idea. Magnetic field, waiting for them to flip. Based on where they flipped, you can discern what kind of functional group may be present. Now this one is important because here 99% of carbons are the isomer, C12 or 12C. 1% of them are 13C. Now it's this very minority that is important for us to tell, or for us to be able to perform a 13 carbon NMR, as these are the ones that will flip for us and give us input as to where the functional groups are present. Okay? So first, we're again going to look at the number of signals, and it's pretty clear here. We have 2 signals, 1, 2. Second, we're going to look at the chemical shift again. So based on that prior graphic, we're going to be able to see that again, this is going to be our carboxylic acid. Okay, it's going to be way downstream, and that again, that corroborates with our hydrogen NMR as it should. Okay, and this one, okay, this points to either an sp3, an sp2, or just an sp, okay, or it could be an alkyl halide, so C to an X. Now, this is telling because an alkyl halide was present in both, or reasonable based on the amount of shift, this one's in this range, based on the amount of chemical shift in both our carbon NMR and our hydrogen NMR. So this is a big clue in that we probably have an alkyl halide. All right, this is really likely to be here, as well as pretty confident our carboxylic acid is here as corroborated with our carbon NMR. Okay, now putting this all together. So what we've kind of been able to figure out is the number of atoms are present. So we have 2 carbons. As we saw, we had the 2 peaks that existed essentially in a 1-to-1 ratio. We had the hydrogens that we know exist in a 2-to-1 ratio, the 1 on that carboxylic acid that we think, and the 2 on what may be the alkyl halide. And then for functional groups, as I just mentioned, but based on the chemical shift that was present, based on the carbon NMR and the hydrogen NMR, it's really likely that we have a carboxylic acid and an alkyl halide. So in putting this all together, let's start with our carboxylic acid. Let's get it down on paper here. Carbon to our OH. So this is your 1H. Now we know this ratio, and we know this 1 is going to apply our carboxylic acid, which can tell us 2 hydrogens that are going to be near our alkyl halide. We can kind of puzzle this together. So we know the carbon that's on our alkyl halide is going to have 2 hydrogens. And counting with this is all the atoms that we've accounted for. So let's just draw our bond here. And this is pretty indicative of what our structure is going to be. Now the big question mark is, what is our alkyl halide? And from this, we actually can't really tell. I mean, we could tell a little bit based on if we had comparisons of the different alkyl halides to each other, and a H NMR to a carbon NMR, and we had different data that we can compare. We may be able to discern it from that. We may be able to, if we use something such as mass spectroscopy or infrared spectroscopy, be able to tell what we're looking at here, but we really can't from just using these 2 tools. So now in unveiling our actual structure, we see that we have 2 bromoethanoic acid or bromoacetic acid, which again follows. We have our 2-to-1 ratio of hydrogens. We have a 1-to-1 of carbons with 2 present. We have our carboxylic acid, and we have our alkyl halide. Okay, so this all makes sense based on our usage of hydrogen NMR and 13 carbon NMR. Thank you so much for watching. Hope you have a great rest of your day.